Okay, so welcome to advanced optimization. This course will be optimization for machine learning mostly. So I just want to say in front in case you are looking for something else. So the topics that I will cover or maybe revise a little bit initially and then I will go to advanced topics are mostly, let's say, foundations. And then we can structure this into first order methods. Then non-convex. Okay, and then maybe some other topics as well. Okay, so the foundations are mostly about convex sets. Some of you may know this already, convex set, convex functions. And yeah, so weak and strong duality. And yeah, optimality conditions. Okay, so this is the first part that we will cover today. Just an overview of where we need optimization in ML. So let us see a picture. So let us see the different applications. So we can put this, one of these is large scale parallel and distributed big data. So in this case it's like we are asking, okay, the methods are scalable or not, okay, for large scale problems. Then in deep learning, GANs, so these are one of the generative models. So basically here, yeah, so mostly algorithms, theory, ML and control. So here we can see some specific cases like reinforcement and so on, reinforcement learning. We don't do these things, but I'm just showing you the overview here. But some of the techniques we learn will be applied in any of these. So reinforcement learning and let's say robotics. So robotics is filled with optimization problems. Okay, very, very challenging ones. Also in probability, if I want to do maximum likelihood estimates, right? So these are optimization problems. So probability and stats. So modeling data and unsupervised learning. Okay, some of the clustering algorithms, right? So they are all could be seen as an optimization problem, and applications are many. Healthcare, okay, transportation, signal processing, biology, and even in interpretable ML. Okay, so here in interpretable ML, yeah, obviously like we are looking whether the model can be interpreted, what is the fairness of the model and so on. Okay, so fairness. Okay, I mean there can be more, but we see kind of applications of optimizations in wide variety of areas, research interest and so on. So what is an optimization problem? Its min fx, and we can have some constraint. Okay, so let us say constraint over x is true, and this we do this min over x. So optimization problem is about minimizing fx. It could be max, but max can be changed to min by taking negative of that, negative of the objective. So essentially everything boils down to this. So here f is called objective or cost. So f is called cost, objective function, loss. Okay, so there can be many names for this f here. Okay, and then we have constraints. This needs to be satisfied, right? Not just minimize, but only those x which also satisfy certain additional requirements needs to be satisfied as well. And this x is our variable. Okay, this is called variable, or sometimes called parameters, or sometimes in machine learning it will be weights, weight vector, and so on. Okay, so this is a very most of the problem will be written like this eventually. So if we look into linear regression, then it's about fitting some curve on a given data, then we fit some, let's say in this case a line for a given data, then this is an optimization problem, because in this case we will be minimizing, let's say we put it a half ax minus b norm square. Okay, so this is the familiar linear regression problem. Okay, it's not linear because of the line. It will be also called linear if it's other curve which is not linear. So it could be quadratic. The point is that A will be some matrix only, right? Even if I use a nonlinear. Okay, so if I fit a quadratic, then these are the samples, and where I want the output y1, y2, y3, y4. Okay, so for the given samples x1, x2, x3, x4, it's my choice which curves I want to fit. So let's say quadratic, then what I'm really looking for is ax1 square plus bx1. So for the same sample, bx1 plus c is y1, and then ax2 square plus bx2 plus c is y2, and so on. So the matrix A here is the data points. Obviously we don't expect it to be exactly equal, so it's an approximation here. So it's all about now transforming this into the ax minus b form. So what we are expecting here, so the weights parameters of our model are a, b, c, so that goes into x, a, b, c, and the data that goes here is x1 square, x1 c, no, not c1, x1 1, x2 square, x2 1, dot dot dot. Okay, and this we expect it to be b, which is y1, y2, and so on. Okay, so then I declare this to be a, and this unknowns as x, and this is as b. So this becomes problem where I want to minimize ax minus b. The reason why I choose a 2 norm is because, and the square here is that I want to make this norm differentiable. If you use any other norm like 1 norm, inherently they are not differentiable. It's not that it will break things. It's just that we have to get subgradients, not the usual gradients. Okay, because 1 norm will be the absolute values, and those are not really smooth functions, so we cannot take a derivative, but indeed we can take a subderivative. So I will define those cases later on, but for the moment let us say 2 norm squared, and it's a differentiable. The reason why I need differentiability is because in optimization methods we use gradient methods, and you need to compute the gradients. Okay, so hence differentiability is useful. Okay, so we have seen one model. So this is already some machine learning model. It's called a linear regression. So here we are trying to fit a pattern in a data, and it leads to an optimization problem. Okay, so this is one of the most basic you can think of. There could be some problems from other domains, but it may need a context. Okay, so it could be, let's say, some signal processing and so on, but it will need some context to describe. But I won't kind of go into that. But let's say from signal processing, one of the problems could be trend detection via total variation denoising. Okay, I will just write down the objective function. Okay, but I won't go in detail. Okay, I will rather ask you to like look up a bit more on this. So there will be some objective functions like this. Okay, when here we are using some signal detection problem. Okay, if we look into some image processing, let's say dictionary learning, then the optimization problem becomes a problem like this, where D okay, and then we minimize over x1 to xn. Okay, we can get into the context of these problems maybe at some point, but just to show that okay, there are some optimization problems behind many of these. There is something called submodular optimization. So it's about product recommendation. So here let V be the set of items. So in this case, I am going to write down again very quickly the model, and S union I. Again, this is a big area, but idea here is like, again, out of what I have already have, let's say I have bought something. So given the next set of items I have, like if I add, okay, can I maximize some objective? Okay, so maybe as a recommender in the recommender system, your goal is to sell a lot more. So if you have bought some Apple notebook, maybe you want to buy some accessories and so on. Okay, so this is again whole area of submodular optimization and so on. But okay, so let us look into mean problem again. So I will go into the foundations today very quickly. So in the foundation, the most important thing for us is something called convex function. Okay, so what are convex functions? They are like ball shaped. So essentially they look like that. Okay, and there is a reason why convex functions are interesting for optimizer, because it's easier to go to the minima. Easier in the sense like there is only one minima. The fact that it's a ball shaped, it will have only one minima. Okay, I mean the moment it tries to come down, it's no longer ball shaped. Okay, to have another minima, it must come down, right? But then it violates the fact that it's a ball shaped, right? So that's why any ball shaped function, we can define these things rigorously, but any ball shaped function will have one global minima. So you are not worried. You can start from some method and then you hit a minima which happens to be global minima. Okay, so before I even go to convex function, which could be defined in terms of convex sets. Okay, so first let me define convex set. Okay, so the first step is convex set, and then I define convex function. So I can define convex sets. A set S is convex if for all x, y in S. Essentially it means that you construct a line joining x and y, and if the whole line is inside the S, then it's a convex set. So then for all x and y, theta x plus 1 minus theta y is in S, okay, then yeah, that's all, okay. So that's called convex set, okay. So from here what do we learn? So this is a convex set, okay. So essentially what I have to check is take 2 points and then make a line and then check whether the whole line is inside the set. It is inside the set here, okay. So you have to do it for all possible points, okay, not just any 2 points. So like let us say this points again inside, these points again inside, these points again inside, okay. So it seems okay, right? I mean okay by just by looking, okay, but of course we will try to prove things okay, in this form. Yeah, yeah, theta should lie between 0 and 1, right. So we keep theta between 0 and 1, okay. Okay, yeah, that's additional we need, because otherwise it will go out. If theta is greater than 1, we are parameterizing the line, so we want the points to be within this, okay. Then theta has to be between 0 and 1, okay. So let us try to prove few results, okay, which I mean convex sets, like which of the things are convex sets and so on, okay. Okay, so we have defined convex sets. So here we have seen that we combine two vectors in certain way, right. So in this case it's theta x plus 1 minus theta y. It's a certain way of combining two vectors, and this is called convex combination. But you also know some other combinations like linear combinations, okay, and so on, right. So if you study linear algebra, then you can combine vectors alpha x plus alpha u plus beta v, okay. So that's a linear combination, right, and there is no restriction on alpha and beta here, okay. In this case there is a special case here. Is alpha is theta and beta is 1 minus theta. Alpha and beta both, since theta lies between 0 and 1, alpha and beta are restricted to be between 0 and 1. So that's the difference between linear combination. Linear combination is more generic, convex combination is more specific. So linear combination would essentially not just restrict u to u and v, it will even go more than that, okay. But in this convex combination, the restriction that theta is between 0 and 1 makes you create a line just between x and y, okay, and not go out, okay. So we have combinations like linear combinations, okay, combinations of vectors. So linear, as I said, so linear is like theta 1 x plus theta 2 y, and this is for x y in C. So this is linear, and then we can have conic, okay, this is a new one. So conic is if we restrict theta 1 theta 2 to be greater than or equal to 0. So this is the most relaxed. This is a little bit restricted, and convex is even more restricted. The convex theta 1 theta 2 both are greater than or equal to 0, or and also lying between lesser than 1, okay. So convex if theta 1 theta 2 lies between 0, or I mean the sum should be 1 as well, okay. So if theta 1 plus theta 2 is 1 and theta 1 theta 2 lies in 0 1, okay. So as you can see, linear, you have seen in linear algebra, you are allowed to take any of these, any, okay, and then you can have conic when you allow theta 1 and theta 2 to be greater than equal 0, and this is even more restricted, okay. So these are the three combinations that we need. Now let us go back to the convex set and let us ask few things, right. If I intersect two convex set, is there a guarantee that it will be convex set, right? So this is a convex set and I took another convex set. So we want to know whether this will be convex, the intersection, right? So let us say this is a circle and this is a square. Intersection, is it convex set, right? So in general, like, can we prove this? Like from picture, it seems to be convex, right? So intersection of convex set is convex. So theorem. So C1 C2 convex set, then C1 intersection C2 is convex. Okay, why is that? So let us use the definition. C1 is given to be convex set, C2 is given to be convex set. So and I'm supposed to prove that C1 intersection C2 is a convex set. So essentially I will take 2 points x and y here, and I have to prove that convex combination of those 2 points is inside C1 and C2. Let x comma y be C1 be inside C1 intersection C2. So this implies x is in both C1 and C2, and similarly y is in both C1 and C2. So basically x and y are in, both are in C1, and x and y are both are in C2. C1 and C2 are convex. So C1 is convex implies that basically any convex combination, right, so of this will be in C1, right. But what are we supposed to prove? We are supposed to prove, so it's better that we write a claim and then we start with that. So what we claim, so what is our end goal is to prove that a convex combination is inside this, because we want to prove that this is convex. So we want to prove that claim is that theta x plus 1 minus theta y is inside C1 intersection C2. Okay, so that's our claim, right? So how, I mean, I'm going to use this, right? So I know that C1 and C2 are C1 and C2 are convex, and x and y lies in both of them. Okay, so if I can prove that this is in C1 and this is also in C2, then I'm done. So essentially what I have to prove that this is in C1 separately and also this is in C2 also. But that seems obvious because x and y are in C1, so and C1 being convex, this is in C1, and similarly x and y are also in C2, and hence a convex combination will be in C2 as well. So here, so since x comma y in C1 and C1 convex, this implies theta x plus 1 minus theta y is in C1. Okay, similarly x comma y in C2 and C2 is convex, this implies theta x plus 1 minus theta y is in C2 as well. Okay, so we use this, both are in C1 in C2, then they must be in the intersection. Okay, so from here the proof is obvious. Okay, now let us look into something called convex hull. Okay, so convex hull, so here let x1, x2, x3, basically it's a convex combination but over many x. Okay, so the convex hull is denoted by CO, x1, x2, xm, and this is convex combination of theta I, xi. Theta i's are greater than or equal to 0, and sum of theta I is 1. Okay, so basically we have generalized the convex combination definition, right? So here in here I only added x and y, right? But I can generalize this convex combination idea. I have theta 1 x1, theta 2 x2, theta 3 x3, and so on, right? So that's what we did, and we impose the same condition that sum of the theta i's is 1, just like in this case sum of these two theta is indeed 1, and each of the theta i's are greater than 0. Okay, so that's also written here. So this is called convex hull, and an interesting question to ask is whether convex hull is a convex set. Okay, so given a set of points x1 to xm, so let us say I take 3 points x1, x2, x3. So if I make a convex hull of this, okay, then the question is, I mean, what is convex hull basically, right here? So I'm supposed to do combinations like that. Okay, so if I'm supposed to do a combination like that, I mean, even before we go to convex hull, we can do a little bit of a linear algebra first. Let us look into linear combinations. So linear combinations of, let's say, two vectors, let's say 1 0 and 1 1. So these are my x1 is 1 0, x2 is 1 1. What if I do a linear combination of these guys, right? So basically alpha I 1 0 plus beta I 1 1. So what do I get, right? So in this case alpha I and beta I has no restrictions, so they can be anything. Okay, so from linear algebra what do we know, right? It's a span of 1 0 and 1 1. Span of 1 0 and 1 1. What do I expect, right? Which space I will get? R2, right? It's clear, right? It's R2, right? If I take a span of this is a basis, right? So this is a basis in R2. It's being two dimensional, right? So if I produce any two independent vector and they are independent, so this forms the basis. So it will be whole of R2. This will be whole of R2, right? And what is in the span? In the span we have linear combinations of these vectors. So if you keep taking linear combination of this vector with different alpha and beta, I will get all the points of R2. Okay, any coordinate you ask me, I can generate by taking some alpha and beta. Okay, now that's linear algebra where your restrictions on alpha and beta were anything, okay, possible. But here we are looking into convex combinations, right? Okay, so you take theta 1 x1 plus theta 2 x2 and so on, but now thetas have your restrictions. Okay, so then what do I expect, right? If I take a convex hull, what do I expect, right? If I take any two of these initially to start with, I have only three points, let's say in this example. Then let's say I take x1 and x2 first. But if I take only x1 and x2, then it should essentially, for different values of theta, I mean, you can say that I'm supposed to add it over all the xi, right? But I can take the third theta to be 0, right? So 1 2, however many points are there are m points here. So in this example I will look into convex combinations, right? So in this case, let's say I will look into theta 1 x1 plus theta 2 x2 plus theta 3 x3. Okay, and I want to know what are these points, right? And given that theta i's are greater than or equal to 0 and sum of the theta i's are 1, in this case sum is 1 to 3. So I want to see which type of points will be generated, right? So if I have like option to choose any theta as long as those theta restrictions are satisfied. So initially what I might do is theta 3 I put it to be 0, and then theta 1 plus theta 2 will be 1. Okay, and we have theta i's are greater than or equal to 0. So if I put theta 3 to be 0, then I have theta 1 x1 plus theta 2 x2, because theta 3 I keep it to be 0 deliberate. Okay, so in this case I want to see what are these points, right? but this is essentially convex combination of 2 points. So this must be the line joining x1 and x2. Okay, so this is the line joining x1 and x2, which is produced by this. Okay, so that's the first step. I do the same thing with this guy. I do the same thing with this guy. Now I have this only the edges in my convex hull so far, but then I will repeat this with many points now. Now I will take this and this. I generated this. Now I take this. I generated this. So basically I will fill this. Okay. Okay. So essentially any point, right? I mean, in the new point, right? So I took this point, the line should be inside. So essentially it's possible to kind of fill up. Okay, but interesting thing is that it will never go out. Okay, it will never go out of this x1, x2, x3 boundary. Okay, and this is happening because of these restrictions on theta. Okay, so from this intuition you can say that convex hull is necessarily a convex set. Okay, so so sometimes maybe you can do some convexification of the set by making a convex hull, and some specific geometric objects are, let's say, half spaces. So let's say half space. So these are set of all x such that A transpose x is less than or equal to B. Okay, A transpose x equals to B is the hyperplane. Okay, we know that, right? A transpose x equals to B is the hyperplane. And when I say negative, then it's like characterizes the points on one side of the hyperplane, right? This is the normal to the hyperplane. Okay, so a plane is characterized by its normal. Okay, and then fact that I'm saying less, okay, then it will be like one of these. Okay, it depends on like the points, which type of angle they are making with A, and also relative to B. Okay, so these points will be on one side. Okay, when let's say it's making some obtuse angle. Okay, and then for these points it will be on the other side. Okay, so of course it's relative to B. Okay, okay, so hyperplane as a set, okay, is a convex set. Okay, because from geometrically it will be one side of the plane. Okay, so indeed in this side of the plane I take any 2 points and then line joining them is inside this half space. So that's kind of evident. Okay, so we may not have to prove everything, and then we can look into polyhedron. So polyhedron is defined to be like this: is set of all x such that Ax is less than or equal to B and Cx is equal to D. Okay, so basically it's an intersection of half spaces and hyperplanes. So these are half spaces and these are hyperplanes. Okay, so again we can prove that this is a convex set. Okay, we can take some points, let's say u and v, and then we can prove that theta of u plus 1 minus theta of v is inside this set. Okay, then there is a object something called ellipsoid. So in ellipsoid we define it to be like this: x minus x0 transpose A x minus x0 is less than or equal to 1. Okay, so this is an ellipsoid, not necessarily centered. I mean, it's centered at x0. Okay, so ellipsoids are also convex sets because they look like this. Okay. If you are familiar with the usual ellipses, then this also comes from there itself. Okay, this is just a vector representation of that. Okay, so if I put a equality here, then it will be some ellipse. Okay, let me do a quick example on that. So if we look into this ellipsoid, then let us say if I take a matrix A, which is 1 0 2 1, then let us look into this. If I say, let's say it's centered at 0, then x0 is 0, then in that case I will look into x transpose Ax is, let us say, 1. Then let us say x is a vector. Okay, so this vector is x1 comma x2, so x1 x2, and A is 1 0 2 1, and this is x1 x2, and this happens to be 1. Okay, and if I multiply this out, then what do I get? So x1 x2, and this is x1, and this is 2x1 plus x2, so 2x1 plus x2, and this will be 1. And if I multiply it further, then it's x1 squared plus 2x1 x2 plus x2 squared, and that's 1. Okay, which is the equation of an ellipse. Okay, so this is a vectorized form because I can talk about high dimensional ellipses. Okay, so in this case I give you an example of a 2D, so that's why I had x1 and x2, and then again if I put this less than equal to 1, then this characterizes the points inside the ellipse. Okay, so now with the points inside, this is called ellipsoid, and ellipsoid is convex. Okay, I mean you can go ahead and prove all these things. This is kind of straightforward. Okay, so I will leave the proofs for you, and then we have something called probability simplex. So probability simplex is set of all x such that x greater than equal to 0 and the sum of xi is 1. Okay, xi's are the components of x. Again, this is also a convex set. You can try this. Now I can define something called cone, and then convex cone. A set C is called a cone if for all x in C, alpha x is also in C for all alpha greater than equal to 0. Okay. So basically it says that any ray starting from the point x, okay, it's a cone. Okay, so if I have a point x, obviously it will hit 0 because alpha can be 0. So 0 vector is here, then alpha greater than equal to 0, okay, will produce a ray like that. Okay, because given a point x here, for x alpha, let's say closer to 0, it will contract the vector. So I can generate this vector, this vector, this vector. I can generate all the vectors all the way to 0, and it's not allowed to be negative, so it will not flip the vector. So it will remain in this direction, but it can go up to 0, and then it can inflate also with alpha greater than 1. So alpha greater than 2x will be somewhere here, and so on. So basically it will produce a ray, and but cone may not be convex because I can have another y, okay, and for y also this thing holds, okay, let's say some beta y, and I can generate all this, and beta greater than 1 also I generate all this. Okay, so I can define a cone which is not a convex like this. Why it's not a convex? Because for these 2 points the line joining is not still inside. Okay, so this is still not a convex set. So I can define a cone. So define a cone to be alpha x beta y and alpha beta greater than equal to 0. Okay, so these are set of all points. Okay, so so this cone is set of all alpha x beta y, alpha beta greater than 0. So this essentially consists of only these 2 rays, and this is not a convex set because, as I said, one point for one line, another point for another line, the line joining them is not inside the set. So this is not convex. So then the question is obviously defining something where a cone becomes convex. So we can say convex cone in that case. So cone which is convex, okay, it's called convex cone. Okay, so the convex cone, a cone which is convex, okay, is called convex cone. Okay, but in general cone is not convex. Okay, okay, and if you are someone who likes challenges, then I will give you some challenging problem to prove that it's a convex set. Okay, and okay, let's see. So this will be kind of like you can try on your own. All the things that I have told you, polyhedron, ellipsoid, it's very easy to prove. You can try. Okay, and but this is very difficult. Okay, so let A be symmetric and positive definite. So this is like d by d symmetric positive definite matrices. Then K is set of all x transpose Ax, x transpose Bx, x is in Rd, is a convex cone. In R2, right, because there are like 2 pair coordinates, right, in R2. We're going to take this as a problem to prove. Okay, it may not be straightforward to prove this. Okay, so that's challenge 1. Challenge 2 is let A be again symmetric and positive definite. Not positive definite. I think positive definiteness is not there. Okay, only symmetric. So only symmetric, and RAB, let us say define this set, is set of all x transpose Ax and x transpose Bx such that norm x is 1, is convex for d greater than or equal to 3. Okay, so what is the additional restriction here? Norm x is 1. Okay, so this is convex for d greater than or equal to 3. Okay, so it seems like, yeah, challenge this will be implied by this is just a little bit harder, right? This is a norm of x is 1. Okay, okay, so yeah, so I will define a few more things. So this is the foundation we are doing to do optimization algorithms. These are the basic things one has to do. So few facts. So a cone K is convex if and only if. So sometimes if and only if is written as IFF. So if and only if K plus K is a subset of K. Okay, k plus k is a subset. So k plus k, I don't mean the same element added twice. It's like any u from k, any v from k, I add them and I get the element in k itself. And this is the if and only if, right? So one has to prove both ways. If k is convex, then this happens. If this happens, then k must be convex. Okay, so these are the facts, like you can try. Okay, even if you don't try, that may not be crucial in this course, but you may kind of like remember this. Okay, and yeah, like few more things, like for instance, set of all xt in R n R plus plus, and such that norm of x is less than equal to t is a cone for any norm. Okay, so a set defined like this, R plus plus is like strictly positive numbers, so t is like strictly positive, and Rn, so x is in Rn, t is in a positive number, is characterized by norm x less than equal to t, and that is necessarily a cone. Okay, so this is all about convex sets. Now we move to convex functions, right? And convex sets and convex functions are related, and they are related via epigraph. Okay, so just a quick, so I have a convex set which is like a ball shaped. I mean convex function I said, right? But I say convex function and convexes are related in the sense that I define an epigraph. And what is an epigraph? Epigraph is the region above the curve. The points above the curve is called epigraph. So now you see this as a set. Okay, this is a set. Okay, and if the set is convex, epigraph set is convex, then your function must be convex function. Okay, so that's how they are related. Okay, so I can define convex function via convex set. If a function is convex, if and only if the epigraph of the function is a convex set. So it's possible to define that way, but that may be a little bit may not be flexible in some cases. So let us define convex functions independently, and the idea here is that the fact is that I want the function to be ball shaped. So the way to characterize this is take 2 points on the graph of the function and join those, and the line should be above the curve. And apparently this thing necessarily makes sure that the function is a ball shaped. Okay, it's a convex function. So that's the definition of a convex function. Take any arbitrary 2 points on the graph of the function and take the line, joining them, then the points on the line are always above the corresponding points on the curve. So for instance, I take this. So for this values of x, the function value is this, but then the point on the line is above the function value. Okay, so and that happens for all the points I'm looking for. Okay, so here also this is above this, here also this is above this, and so on. Okay, now we have to kind of characterize, I mean write this as in terms of definition. So basically for any x and y, or fx fy, the line joining them, okay, the line joining them will be theta fx plus 1 minus theta fy is above the function value. But then these points I will characterize by this x and y, but then I have to go through x and y to trace these values. So I have to take a line here. So this alpha fx plus let's say 1 minus alpha, okay, because it's a convex combination, right? So let's say theta fx plus 1 minus theta fy, so that will characterize all the points on the line. That must be above, greater than equal to f of theta x plus 1 minus theta y. So that will make sure that I am getting these points on the curve. Okay, so now it's very easy to write down. Okay, so using this the notation from these notes, so a function f Rd to R is convex if its domain is convex. Now domain being convex is an essential criteria, because if the domain is not convex, right, so let us say if I make it non-convex, so domain I miss some part here. Okay, so clearly the domain is not convex. So this is my domain from here to here and from here to here. Okay, so what will happen to the function, right, if the domain is not convex? Okay, then is it true that the function will become, I mean, non-convex? Okay, so what role does the domain play, right? If I don't have the domain convex, will it violate, right? Will it violate this line property, right? Because what will happen? Because for certain reason I don't have anything, right? Like I can't even construct this line, right? So for this reason is not defined. So this line itself doesn't exist continuously, right? Right. So I can't check also, right? Right. I can't even check, right? Because the convex definition tells me that take any points on these, right? So I took this and this. That's my choice. Now all the points on the line must be kind of like above, right? But should we kind of like, should we not neglect these points, right? That could be one question, right? So since these points are not in my my domain, okay, so should we not delete those points, right? So can we think of an example, concrete example, where the domain not being convex will create an issue? Okay. Why it's necessary to have domain convex? X is, yeah, so it's like hyperbola, or yeah, xy minus 1, right? This one, or the top one actually, right? Yeah, xy minus 1, right? Right. So what is the problem here, right? So first of all, what is the domain here, right? So what is told to us is like xy is 1, xy is like minus 1. Okay, so I define this over this domain. I define it to be plus 1. This domain I define it to be minus 1. Okay, so overall domain of the function is, does it include 0? It does not include 0, right? So clearly this point is gone. Okay, because at 0 none of the functions are defined. Okay, the one is going to, as we go towards closer to 0 from this side, is going to infinity. So clearly I have to remove this 0 from the domain, and even via this route if I go, then I clearly, function is undefined. So 0 is certainly creating a hole in the domain. Okay, so the domain of this is certainly not convex because of the hole. Okay, so there is a hole here. Okay, and because there is gap here, so this set is like this. Okay, the domain is not a convex set because line joining this and this is not part of that, right? So it's missing one point, right? Any domain, any set with a hole will not be convex. Okay, this seems to work. Okay, so why this seems to work? Like the domain is not convex for sure. Now the next question is, can I like take any arbitrary 2 points and they are like always guaranteed to be above the curve? Not necessary, right? Because I can take any 2 points like here, okay. This is not above the curve. For not just this this part that is missing, like here also, right? If I check here, so this curve is above the line, okay, and here also let's say curve seems to be above the line. Even if I discard 0, because 0 is not in the domain, let's say, so you can say that I am not supposed to check there, but on other points also curve is above, right? Okay, so right. So not a domain not being convex can create issues. Okay. So a function f from Rd to R is convex if its domain is convex, and additionally the line joining them, right? So is convex, and for any x y in domain of f and theta in 0 1, we have f of theta x plus 1 minus theta y is less than equal to theta fx plus 1 minus theta fy. So that's what we talked about, right? So this is the curve values are below the line joining fx and fy. Okay. Okay. So we defined convex functions, right? Now let us see if we can use this to characterize some functions as convex or not. There is a simplified variant of this, and both are equivalent. Okay, so there is another definition of convex, and that is given by Jensen. So what it says is that let f from I to R be continuous, then f is convex if and only if f is convex if and only if it is midpoint convex. That is, f of x plus y by 2 is less than equal to fx plus fy by 2. Okay, so you can say that this is a very special case of that, because there I could have taken theta to be half. So for theta to be half, this is exactly what I get. X plus y by 2 is less than fx plus fy by 2. So, but then this is actually enough. This is sufficient to claim that, and this is true for all x and y. So both are actually equivalent. Okay, we will not prove this, but we will just remember this. So this is due to Jensen. So in some cases you may prefer this, because there is less checking to do, right? The theta is just half, okay, and then you prove it for all x and y. Okay, so this is a basic definition of convex functions, but then we can have a characterization via first order conditions. Okay, so in that case we need f is differentiable. Okay, so if f is differentiable, then f is convex if and only if so if domain must be convex, domain of f is convex set, and so since f is differentiable, now I am going to use some derivative. Okay, so this definition only is applicable when f is differentiable. The original definition of convexity is for even non-differentiable. Okay, that does not look into derivatives of f. So in this case we can say fx is greater than equal to fy plus grad fy x minus y for all x y in domain of f. Okay, and this may look a little bit strange. What am I doing here, right? Fx greater than fy plus grad f x minus y. Okay, this is for all x and y. This is essentially the tangent of the curve at at y, okay, at the point y. Okay, so this is the tangent. So what it says is that for convex functions, wherever I am, okay, so let's say this is y, this is my fy, then the tangent that I have, if I draw a tangent, then all the curve, all the function values are going to be larger above, okay, these tangent values. Okay, so I take one snapshot, then here this is always larger than this above the tangent value. Okay, so we can check, okay, we can check that this is indeed the tangent drawn. So I can give you a hint like how to derive this. So this is a line, okay, passing through y fy, and with gradient. So at this point the gradient is grad f, obviously, right? So at this point the gradient of a function is grad f. So it's essentially like asking line equation of a line passing through y fy with slope. So that's the only thing you need, point through which you can pass and the slope, and that is enough to determine a line, right? So with the slope grad f y. So with this I will say that, okay, you can go ahead and derive that this is indeed the equation of a line. But here I have used a notation. So in this case we see that equation of a line is mx plus c. So you can put these values, right? At y I am at fy, so in place of x you put y, and then the point where you will be fy, so in place of y you have fy. So from the, and m is grad f, so from there you also know what is the gradient. Okay, so from there you get the c value. Okay, so it's a easy thing to do. Okay, so basically it's equation of a line. So this line is fy plus grad f y x minus y. Okay, you can do this derivation. If you cannot, let me know. Okay, but these are like basic stuff, so I'm just kind of like lazy to derive all these things. But okay, so what it says is that there is a line, and above and at any snapshot x, the fx is always above this line. Okay, so fx is always above this line. Okay. Okay, so this is the interpretation of a convex function, but in this case we need access to gradients. Okay, so if I can take a derivative, then this is another way to characterize a convex function. Okay, and this can happen, as I said, always for a ball set function, right? Take this, it is still true. So all like function values at any snapshot is always greater than the line values. Okay, any snapshot is greater than the line value. So this also characterizes the function is a ball shaped. Okay, so there is another characterization, okay, using derivative, right? Okay, so you can kind of go back and forth. Okay, so you can show that this implies the first the basic definition of convexity. Okay, so you can use this to prove to show that a line also will be above the curve. Okay. Okay. And things become interesting if I can do derivative twice. So some functions it may not be possible, but let's say if the function is such that it's twice differentiable, then I'm allowed to do one more derivative. Then what will be the characterization in that, right? If I do one more derivative, it turns out to be even more simple, just one line. I mean, this is also one line, but it's like just one term basically now. So if f is twice differentiable, then F is convex if and only if the domain of F must be convex all the time, right? So domain of F is convex set, okay, and the double derivative of F at x is positive definite, okay. The reason why I say it's positive definite because grad square F becomes a matrix now, okay. So so what happens with the vector calculus? I have a function fx, right? So or let us say I have a function f from Rn to R. When I take a gradient, then gradient of f is n, okay, Rn. But if I take one more gradient, then it becomes a matrix, right? So grad square f is a matrix n by n, okay. And so this condition tells us that the matrix must be positive definite, okay. In other words, the basic definition of positive definiteness is a matrix A is positive definite if x transpose Ax is greater than or equal to 0. Or I mean if we want let us say write it as like semi positive definite, and let us say we use the word positive definite when it's strictly greater than 0, okay. So matrix A is positive definite, and obviously for x equals to 0 it will be 0, but what we are really looking for is for all x non-zero, and for all x non-zero, for x equals to 0 is 0, for all x non-zero still it's greater than or equal to 0, then the matrix is called positive definite, okay. So here what we are saying is that the Hessian, which became a matrix now n by n, let's say, and then we are saying that okay, it's a positive definite, and the positive definite matrices, the other characterizations are that the eigenvalues are lambda I of A, the eigenvalues of A are positive, A are greater than or equal to 0, okay. That's another characterization of that because of the fact that x transpose Ax is greater than or equal to 0, because if there is any eigenvalue with an eigenvector, then I will take that and I will take the corresponding x as v, and then it will imply that lambda will be greater than or equal to 0, right. So I take x to be any eigenvector, x equal to v eigenvector, then what do I get? V transpose AV. Now A is an eigenvector, so AV is lambda v, okay. So this is V transpose lambda v, and I am told that this is greater than or equal to 0. So this is greater than or equal to 0. This implies lambda. Now V transpose V is a norm of V, right? So this is norm of V. So this must, and V can norm of V be 0, right? V being an eigenvector, can V be 0? Norm of V be 0, right? No, right? Because eigenvectors, zero vectors are not allowed as eigenvector, right? So norm is 0 only when a vector is 0. So in this case, definitely norm V is not 0. So the only possibility is like, so this is non-zero because V is an eigenvector. This implies V cannot be a 0 vector, and since V is not a 0 vector, norm cannot be a 0 vector. So since norm is V is not a 0 vector, norm is non-zero. So only way is going to be greater than 0 is when lambda is greater than or equal to 0. I mean, this guy is greater than or equal to 0 for sure, but cannot be 0. So it's like strictly greater than 0. So only way it's greater than or equal to 0 is lambda cannot be negative now, right? So lambda is forced to be greater than or equal to 0. Okay, so this proves that the eigenvalues of a positive definite matrix is necessarily positive or non-negative, right? So this is also interesting because here it's, if you have access to the Hessian, then you just have to prove a linear algebra property that the matrix is positive definite. Okay, so it may be easy in some cases. Okay. Okay, and let us see some more properties of a convex set. So in optimization theory, initial part is like this. Okay, it starts with this. You study a lot of like convex sets and so on, like a lot of objects like polyhedron, hyperspaces, I mean hyperplane, half spaces. Okay, because all this is needed. Okay, they show up as constraint or sometimes in some other ways. Okay, so this is kind of a revision of all this. So one of the again I will state this fact without proving, the pointwise maximum of a family of convex functions is convex. Okay, so this is a fact that we will remember. Okay, so pointwise maximum of a family of convex functions is convex. Okay, so basically we can write this as okay. So we are kind of doing max over y. Okay, so it's a pointwise max, and then if you are not very used to this notation, then what we can say is like this. Let us say G1 is convex, G2 is convex, and so on, and let us say Gk is convex. Okay, then I can take pointwise convex as pointwise max, right? So I take some max, and for which I take the max. Okay, and that gives me some function, right, as an output, let us say. This is what it's written here, but I'm just trying to explain in another way also. So then take some other x. Okay, so same function, some other x, let us say x1, 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 and then you take x2, x2, and so on, and you get some output y2 and so on. So this is essentially a function now. This is what is written here. This is essentially a function now, and then this function that you get will be convex. Okay, and there is a geometric view for this. So let us see a geometric view. Yeah, let us take two convex functions, right? Okay, so both are convex. So let us say this is G1, and let us say this is G2, right? So let us take a pointwise max of this, right? So let us say I'm here, right? So here, what is the max here? I go here, and the max is here, right? So from this pattern, I see that the max is taken by this, the pointwise max until here is this, and from here onwards is taken over by the G1. So far we were getting values from G2, and then from here onward the pointwise max is taken by given by this. So the resulting function that we have now is this. Okay, and what we see is that this is also convex. Okay, so pointwise max of convex function is convex. Okay, this also remains ball shaped, right? So this result is useful sometimes when you look into when we study about dual functions and so on, then this argument is needed at some point. Okay. Okay, so let me define something called indicator function. Indicator function. So indicator function for a set, so for a set X is defined as, let's say I use the notation 1x x, and this is 0 if x is in X and it is infinity otherwise. Okay. So I define some function, right, and what does this function say? It says that okay, whenever the point, so always indicator function is for some set. So in this case this indicator function is for X. So it says that whenever the point X is in the set, then indicate that it's 0. If it's not in the set, then give a very high penalty, infinity. Okay. Sometimes indicator function can be used to remove a constraint. Okay, and I can put this in the objective. So I can eliminate a constraint using an indicator function. So let us see an example here. Now one thing to prove here is that verify that 1x is convex if and only if X is convex set. Okay, this is something we can prove. 1x, and by 1x I mean function, right? So 1x is a convex function if and only if X is a convex set. Okay, so this is what we can prove. Okay, so you can again try this proof. It will be simple proof. Okay, I can already tell you it's just apply the first definition. Okay, and everything works out easily. Okay. And what I was saying is that what is the use of indicator function, right? So I will use this to remove constraints. Okay, so let us see that. So let us see a constraint optimization problem. Yeah.
What is the domain of this?
Is all X, right? All X in X. Okay, domain is everywhere. Domain is everything, right? Because I defined for X and also I defined for anything else also. Okay, so essentially indicator function is defined for all the points. Okay, so if the values of X are coming from R, then indicator function is essentially defined for also not some interval in R, and then it's also defined for something not here. Okay, and good thing about indicator function is that it can be used to extend a function on an extended real line. Okay, so if a convex function is defined only on some interval, then using indicator function I can define the domain over all. That's another use of integrator function. Okay, so my interval is AB, so this is my fx which is only defined for that, but sometimes it's a little bit problematic that I restrict my domain to AB. So that's essentially my constraint here. I want to say why don't you give me a function that's defined over all of Rn, then I will say okay, just add the indicator function there, and it does not destroy convexity. That's the thing, right? So if it's convex, then I will define like this. This is still convex because for other points it just makes this infinity, right? So the curve is not going to go down, it retains the ball shaped anyway, right, for other points, because the indicator function is giving a infinite penalty outside that. So in fact that's already an example that I am trying to minimize a function in a constraint. I want to get rid of the constraint. That's exactly what I'm going to do. So this problem is like minimize fx subject to x is in the interval 0 1. How do I get rid of that and make it an unconstrained problem? I use this integrator function fx plus 1x x minimize over x all of R. Okay, unconstrained optimization problem. Okay, often unconstrained optimization problem are preferred. Okay, because obviously I don't have to like each time check that whether I'm going out. Okay, I start from some iterative method, it may go off. Okay, so those checks are needed in a constraint problem. So indicator function is useful because it allows us to, so in general I have a minimization problem fx and x is in some constraint set x. Okay, then I get to an unconstrained optimization problem, unconstrained optimization problem, and this will be minimum of fx plus 1x x, and there are no constraint on x because now it's defined everywhere. The points where fx was not defined, 1x is defined, well, defined in a very bad way, like it's infinity, but it's defined. Okay, so we can change constraint optimization problem to unconstrained. So that's the good use of indicator function. Okay, so I think we can stop for today. Okay, it's 6:30 already. So see you next time. We are doing this. We will do a little bit of maths optimization. This is essentially a maths course, so we have to do maths. Okay, but applications will come as we go ahead. But before that, we need to build the foundation, right? Okay, then. So thanks.